All right, welcome back, everyone. All right, so for the last talk of the morning, we're super excited to have our own Amy Greenwald here to tell us about her work on learning and regret minimization in extensive form games. So I'll let you take it away.
Excellent, thank you very much. Thanks so much for inviting me. Thanks for all of the workshops. I've been here 6 weeks. It's been delightful. So thank you again. I'd also like to thank my collaborators. It's quite a few. A bunch of them, names you'll recognize, like Mark, who was here yesterday, people at Alberta, at DeepMind. Rika was a student of mine at Brown, now at MIT. And the work that I'm presenting today is primarily from the thesis of Justin Morrill, who is a student at Alberta. All right. So I think we've seen this slide or something like it a few times by now, but I think we'll all admit that there has been tremendous success in recent years with AI learning to play games very well. I guess not just in recent years, but for decades now. All of these games that I'm showing you here on this slide are games of complete information, but we've also seen recent success in poker, a game of incomplete information or imperfect information. So most of the success, a good part of poker success is kind of due to this very influential algorithm called counterfactual regret minimization, which minimizes regret in extensive form games. These are all extensive form games where one player takes a turn, like chess, like you have the whole game tree, one player takes a turn, another player takes a turn, and so on, but we have a whole game tree that we're reasoning about. So counterfactual regret minimization, the key to poker successes there, an extensive form game where there is some hidden information, right? So think about poker, you have your cards and your opponent doesn't necessarily see your cards. So you're playing in a game where part of the state is not revealed. This is quite a monumental, important result for extensive form games. And this talk will be about generalizing this algorithm beyond games like poker, which are zero-sum games, to non-zero-sum games. So just to remind, everybody here knows, I think, but just to remind you all, we have normal form games, which look like this. I think Mark showed the exact same game yesterday, and it came from Wikipedia. So if you're not familiar with it, you can go read about it. Here is a picture of an extensive form game, also from Wikipedia, kind of blurry screenshot. The important thing to notice here is that, and Gabriele talked about this yesterday, talking about the relationship between extensive and normal form games. When we reason about extensive form games, we could, if we wanted to, kind of look at them in their normal form representation, which they do have. But the problem is the normal form representation leads to a blow up, and in general, an exponential blow up. And you can kind of see that in this picture because the normal form representation is showing you, just to explain this picture, we have two players, player one and player two. And player one is moving up here at the top node, they can go left or right. And then player two will move at either of these two nodes, and they have two choices, K and U. So the strategies are functions, you can think of them as functions from these decision points to the possible actions. So what we're looking at here in this representation is, KK here means for player two, when they're at their decision point one, they could play K, and when they're at their decision point two, they could play K, right? So we're listing kind of the whole function, the whole strategy here versus all of the other players, all of their strategies, they have only L and R here, and putting in these payoffs, but you'll notice repeat numbers, right? You have repeat numbers, you have kind of too much information there. So what we want is we want to be able to reason about extensive form games, but in a compact representation, not in a normal form representation, which would lead to this kind of blow up. So that's our goal. We're concerned about the representation complexity. All right, so here is sort of a usual picture a lot of people have talked about. Next slide's going to tell you what regret minimization is. I'm sure everybody knows, but here's my model. So we have a learner. The learner is playing some policy, indicated here. I is us, the learner, and T is the current policy at time T. So that policy, along with the opponent's policies, gets fed into a game, and out pops a utility, which the learner can now learn from. And likewise, the other players will see their utilities and they can learn from them as well. Okay, so one important point is that from the point of view of the learner, whatever the other players are doing and whatever's in the game environment, all of this part of the game, all of this is just, we're just considering all of that to be the environment. I think we've seen that perspective many times this week. All right, and so what does it mean to minimize regret? We've also heard the language of being rational in hindsight used this week. And so what does that mean? Well, it means if the learner is playing this sequence of strategies or policies, pi for policy, I guess, but okay, so what the learner can consider are deviations from their policies. So a deviation here is a function applied to the policy and saying, hey, let's do some other function of our policy instead of our policy. So you can calculate the total utility that's obtained from a policy as compared to the total utility you would obtain from deviating. So by applying a deviation function to the policy at each time. So that gives you your total utility of the deviation. And what it means to minimize regret is to say, well, for some class of possible deviations, for all of them, I could consider what was my utility when I used the deviation versus what was my utility of my own policy. And if the utility I'm getting from using my own policy is high enough, there's a little bit of leeway here, but if it's high enough, I'm happy and I don't have regret. Specifically, I don't have regret with respect to this class of deviations. Okay, make sense? And as we heard from many people, we know how to achieve this. We've known how to achieve this notion of regret for 50 plus years. Okay, great. All right, so what I want to talk about is the relationship between this kind of regret and equilibria in games. And again, this is a bit of history. This is stuff that has been known for the normal form case in particular for a large number of years. So here's what we know. Here's kind of a summary of the normal form story. So there are two kinds of regret that are important in normal form games. They're called external and internal regret. We heard about them yesterday and many other times. And I think by now everyone in this audience would have heard, if they don't know the proof, at least they've heard the fact that if you minimize external regret, you will end up converging to coarse correlated equilibrium, while if you minimize internal regret, you can converge to correlated equilibrium. If you don't know what those terms mean, I am going to tell you what those terms mean in a few slides. But for now, that's just a fact that you have anyway heard several times this week. All right, and there are some qualifiers on the notion of convergence. So it's important to realize that this convergence is kind of in average iterates, or the empirical distribution is what's converging. And actually, it's not exactly converging. It's converging to a set, which means it's always kind of at least arbitrarily close to that set, but maybe not reaching any particular point. Okay, so one paper that I worked on now 20 years ago was asking the question, what if we tried to consider other kinds of deviations besides just internal and external regret deviations? So what if we kind of threw into the mix stronger or alternative or more deviations? Could we then converge to a stronger notion of equilibrium? So we studied this question, and what we found was, first of all, that it was quite easy to consider internal and external regret kind of along the lines of a single continuum. Again, I'm going to show you these definitions in a bit. And moreover, that we could then, and we call this continuum Phi-regret. So that's where the letter phi of the set of deviations comes from. And moreover, that we could come up with an algorithm that was efficient and could minimize Phi-regret for any set of deviations phi. And then we have the natural generalization that you end up at a no, if you have no Phi-regret learning, that you end up at a Phi-equilibrium. Okay, so what the point here is that the set of deviations is defining the set of equilibrium. So here I'm using phi as my set of deviations and phi as my notion of equilibrium. What we saw in the past was external deviations lead to coarse correlated equilibrium and internal lead to correlated equilibrium. But we have sort of a whole continuum potentially here. Yes?
When say efficient for every phi, like what is the set? Like phi could be any transformation?
Yeah, so we're going to come to more details about that, and that's really going to be the focus. So maybe we can hold that and come back to that. But yeah, but we can do efficient, no Phi. It's important that we can do efficient learning in normal form games. So we were kind of wondering, let's throw more phi, more deviations into our bag of deviations, and can we get more strategic power? What we found was that the answer was no, that in fact, the internal regret deviations were getting us all the power that we could possibly get, no matter what we threw into that bag. So that was the strongest form of no Phi-regret learning, and there kind of wasn't much reason to think about other kinds of deviations. Let me just add one caveat here, which is that some people say that swap regret is what leads to correlated equilibrium. So swap regret is a little bit different than internal, and I'm also going to talk about that, but we can be thinking about, no internal or no swap as the strongest form here. All right, so that's the story for normal form games, and that's 2003. Now we move to 2007, and we have kind of a breakthrough in the extensive form game world, where we get an external regret minimizing algorithm for extensive form games. All right, so let me just give a brief idea what external and internal are. So external is the usual kind that, dating back to Freund and Shapiri, and what most of us hear when we say that we have a regret minimizing algorithm, what we mean. We're just looking at the best fixed action in hindsight. So looking at the best fixed action in hindsight in an extensive form game means looking at the best strategy, the best path through the whole tree, right? So that's what it means to have no external regret in an extensive form game. But the problem is that there are a lot of these paths. There are too many of these paths. If you think about it, there are exponentially many paths that you have to compare to. And so the brilliance of the counterfactual regret minimization algorithm was that we were going to compare to all of the strategies in the extensive form game, but we were going to do that efficiently. So without having to enumerate all of these exponentially many strategies. Okay, so that was sort of the cleverness there, and maybe the reason the result was surprising. And we could now solve poker, or come close to, because we had this way of efficiently doing as well as the best fixed strategy in hindsight, being all the possible strategies through the tree. All right. Okay, so that's 2007. And what about now? That was a beautiful result, by the way, again, for zero-sum games. Might have forgotten to say that just then. But what about non-zero-sum games? So von Stengel and Forges thinking about extensive form non-zero-sum games. And what we would maybe like to think about is to think about generalizing the internal case, right? So when we minimized internal regret in normal form games, we found correlated equilibria. And so maybe we can somehow minimize internal regret in extensive form games, and we would find correlated equilibria here in extensive form games as well. I mean, actually, we would do that if we could do that. So the problem, and now let me tell you what internal is, and maybe also swap. So what internal regret means is that when I'm given a recommended action, I'm thinking, or when I'm playing one action, at all the times that I was playing this one action, I don't wish that I were playing another action. So instead of just switching, switching to all of your fixed actions, you kind of condition on what you were doing. And so at the time that you were doing the one thing, you don't wish that you were doing something else. So if we think about kind of how many of these deviations we have, one way to think about it is just if n is your number of actions, that you have n squared of those, right? That you can just kind of go from everything you were doing to everything else you might be doing for fixed actions. But actually, when we look at this in the external world, sorry, I keep getting confused between external and extensive. In the extensive form world, we're going to want to think about swap deviations. And there are going to be way more of the swap deviations, and the swap deviations are going to cause us difficulty. Okay, let me clarify. So what are swap deviations? I told you what internal are. Internal is like whenever I was playing one action, I don't wish I were playing something else. Swap is just thinking about all the ways that I could transform any of my actions to any other actions. So actions in extensive form games are now these kind of whole full strategies on a tree. So if we try to think about all the ways we can transform one of these things to another thing, we have like lots of exponents and way too many things to consider. So we would like to minimize swap or minimize external internal regret in extensive form games. The problem is that we're gonna find we can't do that efficiently. There are just going to be too many of these, and that there's not going to be an efficient algorithm for doing that. And this was recognized already in 2008 by von Stengel and Forge. Did someone have a question?
Yeah, I mean, this is Drew. I have a question.
Yes.
So you're talking about the regret in these extensive games. Can you explain how that's computed? I mean, do players know the strategies other people are using, or are we having to base this based only on what they saw in the game? I don't understand. I mean, I know what regret is for Hanon or in a normal form game, but I don't understand how you're using the term here.
Okay, excellent question. So I think you're asking whether I'm kind of in a Bandit setting, or what's the word for the opposite of the Bandit setting? The full information setting. Is this the question?
I don't know the lingo, but yeah, with an extensive game.
I mean, okay. I
just
think
tell me what people observe at the end of each period. What's the data that's used to compute the regret?
Right. Okay, so in practice, these games are very, very large, and we can't actually visit the entire tree. But for the story that I'm telling now, I'm kind of imagining that we're visiting the entire tree and that we're in just a full information setting, which means that no matter what strategy we employed, maybe we saw, what would have happened if we did something else.
Perfect. Thank you. I suspected that was the case, but since you have extensive form up there, because fine, we can discuss this over the break.
Okay. So extensive and expensive, I think I heard. Expensive form also. Yeah. Okay. Okay, so yes, let's just imagine we're in the full information setting. I mean, on my last slide, I will say future work, let's extend this all to the Bandit setting. All right. So, okay, so there's going to be too many internal or swap deviations in the extensive form world. And so von Stengel and Forge recognized this, and they proposed two possible ways to sort of simplify the story, or to maybe, to not consider all possible internal or swap deviations. Okay, so remember, we're like kind of throwing more stuff into the bag so that we can compare against more kinds of deviations. And we've already achieved external. And we know that external will get us to coarse correlated equilibria if we minimize external, if all the players minimize external regret. So we're saying, can we get something stronger than coarse correlated equilibrium? Can we do something more? Can we put more stuff in the bag, but we can't put in all the internal deviations? So it's going to turn out there's this vast landscape of possibilities that we can consider here. And we'll consider a bunch of them today, and there's more to potentially consider. All right, so here is a simplification that came from von Stengel and Forge. The first one, behavioral deviations, which I seem not to have defined yet. Okay, well, I'll define in a few slides. And a second one that they also introduced, which are now called causal deviations for the most part. They called them reduced strategies. We call them causal deviations. All right, so something very exciting happened. So from 2008 to 2020, I think maybe we were all asleep, something like that. But then in 2020, very exciting work by Gabriele and his colleagues, they developed an algorithm that could minimize regret for something stronger than external, called causal, or for reduced strategies. They had an algorithm that, therefore, because it's minimizing the stronger thing, was actually getting more strategic power and converging to a tighter equilibrium concept than coarse correlated equilibrium. So it's not full correlated equilibrium. It's called extensive form correlated equilibrium. It's something in between. So that was a very monumental and exciting development. So what this work is about, what we've been thinking about, is kind of my same story that I was thinking about in 2003, but now in the extensive form world, which is, what else can we put in the bag here? What are other kinds of interesting things to think about? So let me just say that behavioral, which I'll tell you about in a minute, is kind of the upper limit. So behavioral is a restriction of internal and swap, but we also can't do it efficiently. So it's sort of at the top of what we're thinking about. And then there's causal, like behavioral is up here somewhere, and then there's causal, which is down here somewhere. And then there's like maybe a bunch of stuff in between. So we know we can do causal, we know we can do counterfactual. There's something else called action, which corresponds to an agent form correlated equilibrium. If you've heard of that, that was in von Stengel's paper as well. Those things are all down here somewhere. And then there's behavioral up here, which we can't do. And then there's sort of a vast landscape in between. And that's what this paper is about. We're exploring this landscape in between. it's pretty freaking complicated. But there's interesting things to glean, I think, from the story there. So yeah, we can't do efficiently. That's what I mean. Well, I mean that we have too many possible deviations to look at, and so.
But is there a complexity itself associated with it?
Oh, okay. Oh. Should I say I don't know how to do it efficiently?
I mean, so.
That's a good question.
So from Stengel, I think they had a result about optimizing over equilibria, correlated equilibria. But do they have, is there a formal?
But did they do it?
So they had a hardness result for optimizing over correlated equilibria. But is there like a hardness that says that I cannot find any correlated equilibria? Like, yeah. That's
Yeah, it's a good question.
Yeah, I don't know off the top of my head, but like I think all the people that I talked to, like I think it's pretty believed that this one maybe that swap regret in ExtensiveForm games is hard. So basically finding just one normal form for the equilibrium even.
It's expected, but no formal.
Right.
Maybe not.
I mean,
Yeah.
maybe there is a way to compute one normal form correlated equilibrium in ExtensiveForm games without using swap regret. So maybe like dynamics are hard, but not the computation. But yeah.
So we look forward to the hardness result of the reunion.
Noah, you're on. Yeah, so the number of deviations, there's so many deviations, but maybe this is not enough of an argument because for CFR, you could think of it, there's too many deviations and yet we had a clever way to do it. So again, I mean, here it's showing up in a little bit of a different place, which is why I'm slightly more confident that it's still, we would have a hardness result, but I guess I don't have a hardness result. Yeah, not my department. Okay, so here we are with same story, trying to generalize from 2003. Here we are in 20 years later, and trying to throw more things in the bag, trying to figure out what we can throw in the bag and maintain efficiency, believing we have an upper limit on what would be efficient. But I guess that remains to be established. All right, and so what we develop is an algorithm which we call ExtensiveForm regret minimization. And you give your ExtensiveForm regret minimizer a choice of phi. This is kind of how our Phi-regret algorithm worked. We could give it any phi, we could minimize regret, it would converge to the corresponding equilibrium defined by that phi. So we're gonna do exactly the same thing here. We're gonna have whatever our class of deviations is, we'll feed it to our ExtensiveForm regret minimizing algorithm. It will minimize regret with respect to those deviations, and we will arrive at some equilibrium corresponding to that phi. So the important thing is that the phi itself defines the equilibrium. Okay, and we have two important special cases here of this external ExtensiveForm regret minimizer. All right. Yes.
Is there a way to qualify like the spectrum of the phis, like on one end and the other, like what's in between?
Right. So I would like that. And so when I said that it was pretty freaking complicated, it's because I don't have that. But maybe there is a cleaner formalism in which we can understand all of these. I'm just going through examples. Most of this talk is examples. I can tell already I'm gonna run way over. So everybody who wants to stay for lunch and have lunch here, I'll go through all my examples with you. So trying to get our head wrapped around what might be a nice clean way to generalize this. All right. Here's what's coming. Let's do that. All right. So definition of correlated equilibrium. I think most of us know this. I'll just tell you very briefly. One way to think about it is that you get a recommendation. Each of the players gets a recommendation. And when they get a recommendation, so if your recommendation is chicken, conditioned on seeing the recommendation chicken, you can do a Bayesian updating step and sort of infer what your opponent is going to be doing. So if the equilibrium is a third, a third, a third, just on these cells with positive probability, if you get the recommendation chicken, you know that your opponent is doing half chicken and half dare. And so with those probabilities, you calculate your expected payoffs for chicken and your expected payoffs for dare, and you find that you prefer to play chicken to dare. Okay, so that's the way I think about correlated equilibrium, and that corresponds very nicely actually to the way I think about internal regret. This is for normal form games. Okay, so that's correlated. Here is coarse correlated. So coarse correlated, no recommendation. There's just the distribution. So here's kind of a funky example because it puts some weight on this negative cell, which you don't really want. So sort of demonstrating that maybe coarse is not the greatest solution concept out there. But here we have a third, a third, a third on these diagonal. So if I'm the row player, I know there's a third, a third, a third on A, B, and C. And so I do the same thing. I calculate my expected rewards. Obviously, if I play C, I get something negative, but calculating my expected rewards for A and B, those turn out to be 0. So I'm perfectly happy to just go with my a third, a third, a third, which would have given me a payoff of 0.3 in this example. Okay, so we're considering versus the best. Here we're looking at the best fixed action, the best action in hindsight. So this is kind of the relationship between external regret minimization and coarse correlated equilibrium. Okay, here are some beautiful slides from my talk in 2003. All right, so here's how I still am thinking about deviations in normal form games. So they are ways of transforming an action. So here we have our set of A actions. So we have a function from actions to actions. And maybe the easiest way to picture this is as stochastic matrices. And so what these stochastic matrices are doing is they're action transformations. So they're telling us that if we have, for example, this external matrix, so this matrix is going to decide that rather than doing whatever you're doing, you should just play action 2. So we represent that as a stochastic matrix, which we multiply by our probabilities on all of our actions, and we end up with all of our weight on action 2. So this is how we represent the external deviation to action 2. And if we want an internal deviation, in this case from 2 to 3, we have almost the diagonal matrix, but we take all our weight on 2, I guess that was here, and we move it to 3. Okay, and hopefully I got my left multiplication right. Okay, so if I multiply my current strategy by this matrix, what it does is it takes all the probability that I had on 2 and it moves it over to 3. Okay, so that's how I transform action 2 to action 3. So we have stochastic matrices that are representing our internal and external regret. Okay, great. So with that, there's a beautiful algorithm from, I was going to say from Blackwell, but maybe not from Blackwell, maybe from Hart and Mascalel, satisfying Blackwell's approachability condition, which luckily we heard all about yesterday. So we just don't even have to do this. So I'll skip it. But the important thing that I want to tell you is about the regret matching algorithm, because it's just a very intuitive and quite beautiful algorithm. So here is the regret matching algorithm. So what we have here is we have a bunch of regrets and we have them in phi space. So that means we have regret for not playing our first deviation, our second deviation, our third deviation, all the way up to our 5th deviation. So we have a whole vector of regrets for not playing any of those deviations. We'll just look at the positive part of those regrets. And now what the algorithm is going to do is it's going to take as input our phi matrices. So you can think of the internal, the external, some combination of them, whatever you want, some kinds of matrices, takes as an input those phi matrices, and now it computes this convex combination. This convex combination says, let me, if I have a lot of regret for, my 5th deviation, let me actually weight that transformation by the regret that I feel for not having employed that deviation. So this is computing a convex combination where it's putting weights exactly with respect to whatever the regrets were for not using that deviation. And then it turns out that finding the fixed point of this matrix is enough to exactly satisfy Blackwell's approachability condition so that we can get a regret minimizing algorithm. So that's how regret matching works, and that's how it kind of puts these matrices together in this clever way to minimize regret. Here's a proof. You can see here's a pi and here's pi, and goes to 0. If you use the fixed point, you get 0, which means you're like right on that hyperplane that you wanted to be on. All right, so one more ingredient we need now for extensive, God, I can't get that right, for the extensive form game setting, and that's something called time selection with regret minimization. So time selection is like this kind of funky thing where, so if you think of all of your fees, if you think of them as experts, which we sometimes do, then this has to do with kind of maybe waking up some of your experts or trusting some of your experts more on some of the days. So for example, if I need to commute to San Francisco from here, I might, and I'm going like on some weekdays and sometimes going on some weekends, right? I might use a different expert to tell me the best route on weekdays than I might on weekends. So what time selection is doing is it's allowing me to figure out which experts to pay attention to, kind of on, or maybe allowing me to figure out, you know, which experts are really, sorry, that's not right. I have to be able to, regardless of who my expert is. So the time selection is going to be for all possible weightings. So for who's ever awake and who's ever asleep, right, at a given time. I want to be able to, with respect to all of those experts and all of these different times when I wake them up and put them to sleep, or in general, there's just probabilities on them. But I should achieve the same kind of no regret condition I had before, but with our weightings involved, and of course, with respect to all our deviations and with respect to all of the possible weightings. I don't know, that was kind of a bumbled description, but maybe people have an idea what this is already. All right. So just another beautiful slide showing that I can sort of insert my weights everywhere, and I will still be able to do a Blackwell thing with weights. All right, we'll need those weights later. Good. Let me pause for any questions, because now we'll get into our part of the story, which I probably am out of time already. Does anyone know what time it is?
Close to 7.
And how much time do I have?
I mean, technically 8 minutes, but like,
8 minutes.
no, I mean, it's
Okay.
like we have a big lunch break after this. I think it's
Excellent.
Like another like 10. 15.
Okay, but if people want to go, I'm not offended. So please, if you have to go, you just go. But I could go on for another hour. So I'll just plan on that and everybody just leave as what it was. All right, so here we have an extensive form game, and now we're going to do regret minimization and extensive form games. All right. So let's see, what's important? What's important here is that we have an information set. So this is a place where one of the cards, yeah, the cards were handed out. So what do we have? Player 1 got a queen. We can see in both of these, player 1 knows they have a queen, but they can't tell what player 2 got. Player 2 might have a jack and player 2 might have a king. Okay, so this line is kind of indicating that player 1 is, you know, in a confused state at that moment between what player 2's cards might be. So that's an extensive form game, and this is where we now want to minimize regret. So here's kind of a more abstract version of that picture. I'll just do a little plug for a model that we've been working with, which we call POPs. This question came up a lot. That's why I've added this slide. But here's the game. And what we do, what all of us do when we reason about extensive form games is we kind of reason from the point of view of one of the players. So what this POP model is doing is giving us a formalism in which to reason about just one of the players. So that's what I'm showing you here is like, here's player 1's possible information sets or decision points where they need to make their moves. And here's player 2's over here. And so we just kind of break this thing up into everybody's different point of view. The real reason I put this in was I wanted to make a plug for everybody to come to RLDM, which is happening in June in Providence. So RLDM stands for Reinforcement Learning and Decision Making. And I thought this paper was there, but then it turns out this paper wasn't there. This paper was somewhere else. So, but everybody should come to RLDM anyway, if you can. RLDM is this wonderful conference, which is like what you could imagine NeurIPS was like 20 years ago. So it's just neuroscientists and reinforcement learning researchers coming together in a much smaller, more intimate environment. All right, please come. Okay, so here we are with deviations and extensive form games. Okay, so here I'm showing you swap deviations. So here's a picture of a possible strategy in this game with 5 nodes in our POP formalism. And there are 32, 2 to the 5th possible strategies in this game. And now if I want to consider all the ways that I might, change from one to another, I end up with 32 to the 32 of these deviations, which I'm just going to say is too many. I don't have a proof. So, okay, so those are the swap deviations. So we have to reduce. So how are we going to reduce? So here's the reduction for behavioral deviations that von Stengel and Forge introduced. What they said is that when I'm considering my recommendations at an information set, those recommendations can kind of only depend on what I've seen so far in the game. So I'm playing over here, and I've been getting these recommendations and maybe following them, maybe not, but I can't kind of condition or think about what's happening in some other part of the game. So remember the definition of correlated equilibrium, like we got our recommendation and then we did this Bayesian updating, and then that gave us an idea over what everybody else was doing. So in this behavioral deviation world, I'm going to see my recommendations along the way, but I can't use any information from any other part of the tree. If I have to think about all that stuff on the other part of the tree, that's where we're it's getting too big. Okay, so that's the reduction that we're making. And let me just show you in an example of kind of what we're missing by looking only at behavioral deviations. So here is an example of a game, which is a bit like matching pennies. So let me explain how this is written. So we're looking at payoffs from the point of view of player one. Those are the payoffs down here. And there are two possible recommendations. They happen with probability 50-50. So in this, the recommendation is the bolded stuff. So in this recommendation, player one is recommended this stuff that's bold, and player two is heads. And in the other recommendation, player two is tails. So the point of this example is that this is in fact a behavioral correlated equilibrium, even though there's kind of this unfortunate thing happening where in recommendation one, player one is getting only -2 payoff. So if we look at the swap deviation, we can see that there's an opportunity for player one to do better. Instead of following this recommendation over here, they can go ahead and switch to playing H and they would get +2. But the reason that the behavioral deviation rules this out is because the only way that player one can figure out that it'd rather swap over here to H is based on this other stuff that's happening in another part of the tree where player one didn't go, where the recommendations didn't go. So over here, well, under recommendation one, right? So we came over here in recommendation one, and the only thing that's different, right? Because recommendation one is the same as recommendation two. Everything is the same here. But the only thing that's different is when player one got here, they had to look at this other part of the tree that they didn't go to in order to, can you see what I mean? Like here, this is an H, and here, this is a T. So you have to condition on information in a different part of the tree where you're not in order to figure out that you wanted to make this swap. Does that make sense? Like the behavioral deviation rules this out. You're not allowed to look at what's happening in this other part of the tree where you didn't visit. Yeah. How is which different? So EFCE is going to be a special case of the behaviorals. So probably, I didn't check, but this may be an EFCE also.
What exactly is the distinction?
These are great questions, and we're getting there, I hope. Here, we already got there. That's great. Okay. All right. Any other questions on this example before I answered that? Okay. So here is a picture of known basic behavioral deviations in EFGs. This may be as far as I have time to get. I mean, this and a couple of examples. This may be as far as I have time to get today. But let me just tell you that I have a much uglier picture with way more stuff kind of in between here. So like we were trying to put more stuff into the bag and get stronger while maintaining efficiency, get stronger convergence. All right, so here's how to read this picture. So we have three kinds of things. This is our key over here, right? So we have trees, we have sequences, and we have actions. We also have three colors. So the black color means identity, which means you've been given a recommendation and you follow your recommendation. The red means you deviate. This is like an external deviation. You just go do whatever you want to do. And then the blues are things that are recommended. So for example, internal is I got a recommendation and I switch to another entire tree, like some other thing completely, doing that instead. Okay, so those are the internal transformations in the extensive form game. Down here we have external, which is just like I go and do any of these strategies, all fixed in hindsight, whatever, any one of them that I want. So over here we're kind of counting how many of these things there are. So external, we got this number, and internal, we got that number. You can think about these things, and we can talk about them later if there are questions. But a problem is these I exponents. So I is the number of information sets. So those were the decision points in our pops. Okay, so we don't like i's in exponents. That's bad. Okay, so here we have i's in exponents for external, but we said that CF stands for counterfactual. There are not i's in the exponent for counterfactual. So counterfactual again is like this great miracle, because without having an I in the exponent, we managed to minimize external regret. Okay, so let's discuss this picture a little bit. So up here at the top, we have internal. And here's the kind of ones that we've talked a little bit about so far. So causal are the ones that define EFCE. Okay, so EFCE stands for extensive form correlated equilibrium. I think when von Stengel originally defined extensive form correlated equilibrium, he might have been referring to what we're now calling behavioral correlated equilibrium, anything defined by any of these behavioral transformations. However, the language has kind of stuck. So EFCE is referring to the causal transformations. Okay, so what is causal? So causal says we've been going along and following recommendations for a while, and now we consider when we get some this is an informed causal. You can be informed when you have these blue lines. So I get a recommendation and I decide, oh, well, I'd rather do something else instead. So this is what's happening right here at the bottom, is whether I'm using one of my n squared transformation matrices for all of my internal transformations, or if I'm in the blind case, I'm just using one of my n transformation matrices. I guess I should say one other important thing, which I would have said at the end, but I don't have time, which is that the counterfactual regret minimization algorithm is kind of, it's amazing in what it achieves, but it's also super simple. Like, it's a super straightforward idea, what it does. I mean, all it does is take your regret minimizing algorithm and run it at every single one of the information states. That's all it's doing. It's just running a regret minimizer everywhere. I mean, it's running a regret minimizer with, long-term information, which is what Drew was asking about earlier. It's assuming that somehow it has all the information it needs to run those regret minimizers, but all it's doing is running those regret minimizers locally everywhere. Okay, so that's how the algorithm is running. So I just mentioned that because you could locally run an internal regret minimizer or an external regret minimizer. Counterfactual regret was always running external, but this picture is saying, hey, what if you run an internal there instead of an external? Okay, so the difference between causal and counterfactual is the following. Causal follows recommendations first, then maybe gets a recommendation or maybe deviates with one action. And then after causal deviates, I think I skipped that on the earlier slide, but what von Stengel said for reduced strategies was after a deviation, no more recommendations. Like, that was the second way of limiting, of finding a more restricted class of deviations. So you follow for a while, you get a recommendation, but if you deviate from that recommendation, it's all over for you. You won't see anything else in the future. So thereafter, you're in an external world, you're just on your own. On the other hand, counterfactual is kind of this funny thing where you decide, hey, I'm just going to deviate someplace. Then maybe I'll get a recommendation, maybe I won't. And then after I deviate someplace, I'm going to recorrelate. It's going to get to recorrelate. So that's kind of the idea. Like, recorrelate means like go back to following recommendations, go back to identity case. Okay, so can you see that causal and counterfactual are somehow inverses of one another? And so the more general thing that we're going to have on this slide that I'm not going to get to is going to be something that starts with black and then, gets some recommendations here, then does some red and maybe gets another recommendation here and then goes back to black. Okay, so that's like our best algorithm, actually. The one that minimizes regret with exactly, like, cross out this red triangle, minimize regret with respect to that picture that I kind of just highlighted. Okay, so that's kind of the strongest form of deviation that we have so far. well, you could do stronger, but every time as you do stronger, there's some cost in your efficiency of your algorithm. Okay, so now, Noah, can you ask your question again, or do you want to see some examples? Now we have some examples coming of what, like that would distinguish these equilibrium concepts. All right, so one thing to say is here's a picture kind of showing that these things, every single one of these defines a class of equilibria, right? All of these different ways that you can deviate, it's a phi. So we have the Phi-equilibria when we minimize regret with respect to these kinds of deviations.
What do you call informed line?
Yeah, that was just what I was mentioning before, if whether we're using internal or external regret matrices at each of our information sets. So like, am I potentially seeing another recommendation before I, does that make sense? If I'm using n squared or just n matrices at each, okay, yeah, that's the only difference there. Oh, I didn't mention action, but action is also something that von Stengel studied, and actually it doesn't imply, right, so these are all implications, that's what I wanted to say. So this is our strongest, this is our weakest, so up here we have correlated, here we have coarse correlated, here we have something we just called it behavioral. This is behavioral correlated equilibrium, this is EFCE, and this is counterfactual, and then action is just sitting out here in outer space, not implying external, but all of these are implying coarse correlated. You can see from this picture that EFCE is stronger than coarse correlated. So the next slide, this table, is showing us actually that these two columns are distinct. So counterfactual and causal equilibria, we have examples where we satisfy one and we don't satisfy the other. And so I don't know if we really have time to go into the, I could go for another hour. So I don't know. I should wrap it up. Okay, I have these examples. I'm really happy to share them with anybody who wants to see them. So these are examples that will differentiate between causal and counterfactual, which I've told you are distinct. Okay. Then I have a little bit about the algorithm. Won't have time for that. Won't have time. Okay, I'm just going to wrap up. I think I've told you a lot. There's a lot more to say. That's the really ugly picture. Okay, so let's just make that go away. Bless you. Yeah, that causes people to, I don't know, get sick or something. The sight of it. Yeah, but here's the strongest deviations we've been playing with. We call them twice informed, and that was sort of the merging of the two pictures. And I'll just close by showing you some experiments here. These experiments are, we can, if we want to, implement behavioral on these very small games that we've tested so far. So here's behavioral up here at the top. It's getting the highest rewards in these examples. We can also look at any of the ones in that picture. We've implemented them all, right? All you have to do is give a different set of deviations to these to the algorithm, and you end up with a different, it's a very general algorithm that's parameterized by the deviations. So here we can see that TIPS, which is the one that we had up top there, the twice informed partial sequence, that's doing, in some cases almost as well as behavioral. It's a little more expensive than the others. This picture is kind of amazing to me and surprising. Like here, this pink line above here is counterfactual. So in that example, counterfactual is actually doing better than TIPS, which I didn't expect. So that requires further investigation.
Wait, is it because of non-convergence or what? Like, I thought TIPS.
It's more deviations. Yeah, right. So does it seem like a bug? Yeah, maybe. I don't know. It's surprising. Yeah.
Why does convergence to a stronger equilibrium concept imply better reward? Couldn't there just be worse equilibria in the stronger concept?
Yeah, there's an equilibrium selection.
Yeah. So you're just wandering around the space, but you're wandering around a smaller space, maybe with lower valued equilibria. Yeah, that's right. Like if you're in a bigger space, you can get higher valued equilibria. Okay, no bug. I don't really think there's a bug. Justin is very good.
Yeah. I mean, like also, like if you have to be robust towards, like against more deviations, it might take you longer to learn like a good equilibrium. So it might be like convergence also kind of like question.
I see.
Like even like in terms of like
but it looks pretty flat. But yes, yeah, it's not really changing, but maybe there would be some change down the road. Yeah. Okay. I have a summary of my whole story, but I've gone on enough, so I'll take questions. Oh, wait, sorry, one more thing. This is very important. Okay, so, yeah, just future, what are we doing next? So we've implemented this algorithm on small games. Of course, we want to solve big games, right? People were talking about Hanabi, people talked about diplomacy, these kinds of games that we would hopefully like to solve. And eventually we'll try to scale up EFR. We'll have to do all this stuff. CFR has been very successful, but with lots of bells and whistles. So we'll have to spend 10 years adding bells and whistles to EFR and then see what EFR can do. So we'll get started on that soon. But in the meantime, our picture is very complicated, right? So we're looking at a very complicated story here. And I think, this is the best that our best intuition about a trade-off. I mean, this is just an intuitive thing where Dustin really, implemented exactly this set of deviations between behavioral and the stuff down here. But that's not necessarily the right answer, right? So there's a vast space in here, and maybe there's a simpler picture. Maybe there's an easier way to understand everything going on here. And the real question that we want to answer is, what's the largest, assuming the conjecture that behavioral is too expensive, right? That would not yield an efficient algorithm. So assuming that, or maybe not even assuming that, what I was going to say is what's the largest class within behavioral, but really more generally, what is the largest class for which we can have an efficient no regret algorithm? That's the open question. Okay, thanks.
Well, thanks a lot. Yeah, that was a really fun talk. Do we have any questions? Yeah, just.
So at the risk of keeping you longer,
I can stay. Everybody else.
I guess could you give us just a hint of the ideas for the design of the algorithm? I guess I don't know if that's the right time to do it, but just.
Yeah. I could, but we'll have another few minutes. Any other shorter questions? But I will. Yeah.
Yeah, short question.
Yes.
So in your experiment, are you showing the last iterate or?
Oh, no. That was, yeah, those are just the average rewards. Oh, yeah. Oh, okay. Actually, right. We're not showing, Dustin, are you on the call?
It's in chat.
Sorry?
On the side, you say average failure.
I still need the answer. Who's here? Is he there?
Let me have a look.
Ask him what we're plotting exactly.
Oh, sorry. Justin said he couldn't hear the question.
Right. Okay.
Yeah.
What
Maybe you can repeat the question.
Yeah, Dustin, we're just curious a little bit more about the experimental setup and what exactly we're plotting here. When we say average payoffs. I think we can hear you if you talk, if you unmute yourself.
I'm not sure if we can.
Oh, okay. No.
Hello, can you hear me? Sorry.
Yes.
Okay, yeah, so it is the average reward while the agent is learning. On the left set of the left column, that's where the opponents that the agent is learning with are static. Like they're not responding to what the agent is doing. It is a sequence of strategies that changes as like over time, across rounds. It's just not reacting to the way that the agent is behaving. For the results on the right column, all of the agents are learning together simultaneously.
Okay, thanks.
And are these like what type of games are these, like alternative or what games are they?
Dustin, can you say a word about the games too, about Goopspiel and Sheriff, if they're zero sum, non-zero sum?
Sure, yeah. So the first Goofspiel game there is zero sum and 2-player. The second Goofspiel is 3 players and non-zero sum. And then Sheriff is 2-player non-zero sum. They're all imperfect information games. Yeah, Goofspiel is a pretty classic card game. And Sheriff is like a small, miniature version of the Sheriff of Nottingham board game, if you're familiar with that.
Let's see. Are there any other questions?
No.
Oh, okay, sorry, I didn't see it.
One quick question. So the blind causal one, is that, I think, is that sometimes referred to as EFCCE? Then the informed causal is EFCE? Is
Yes,
that the right
exactly,
correspondence?
exactly. Yes.
Okay, thanks.
Yeah, thank you. I didn't even mention, thanks. Yeah, so in that whole table, that's a good point. Yeah, so when we have informed, we're getting to CEs, and we have blind, we're getting to CCEs. And that's exactly a function of which matrices we're using at those information sets. Yeah, I'm happy to stick around and talk about the algorithm.
All right, yeah, but maybe we should stop it there and let people go to lunch. But yeah, as Amy has said, she's very happy to keep telling you about it if you want to,
Stay for another hour.
talk to her. Yeah. All right, thanks a lot. Let's thank Amy again.
Thanks to all of you for staying. Sorry to keep you from lunch.
No, it was a very fun talk.
Great to see all of this together. I took it forward.